Hello everyone, I'm Norman Wahlberger. And in today's famous math problem, we're going to look at Japanese temple problems. This is going to be the first of a number of videos that I'm going to devote to this interesting topic. So they're called Sangaku in Japanese, and it's a tradition that arose roughly in the year 1650 to 1850, sort of the Edo period of Japanese history, where geometry problems were posted on wooden tablets and they were hung from the eaves of temple roofs. We have about 900 of them that remain from that period. And we also know that they are written in kind of an old style of Japanese called kanbun. Some people say it's maybe a little bit analogous to Latin. Anyway, it was a little bit of a learned language, and so most of them were written by samurai or relatively well-educated people. But they would have been seen by a wide spectrum of society because they were hanging there very visibly from the temples. The problems were actually often quite original and are a marked departure from the kinds of geometry problems that we find in Western texts. These problems often involve circles and ellipses very prominently, and some of them are quite elaborate. The one we're going to talk about today is a relatively simple one, but later on in the series we'll also tackle some more challenging ones. The proofs were sometimes sketched in these hangings, but sometimes they were left to the reader sort of as a challenge. The problem that we're going to talk about today is a relatively simple problem, and I'm going to encourage you to have a go at it as well. But it leads to some interesting discussions, and we're going to, in the course of looking at this problem, investigate some things that will be novel even for probably professional mathematicians who are watching. Okay, it was posed by 13-year-old Sato Naosue. Not sure if I'm pronouncing that right. And it was hung in the Akahagi Temple in Ichinoseki City in 1847. So relatively late in the history of Sangaku. Here's the problem. It concerns a right triangle, ABC. And in this right triangle we have here a square. Okay, and the square BDEF has inside it a couple of circles. So here there's two equal circles of radius r, symmetrically placed, and on either side there are two congruent circles of radius s. Now, on top of this square in the triangle, there's another triangle, of course, and the in-center circle of that triangle there has exactly the same radius as do these two ones here. And here on the other part of this triangle there's another in-center circle, and it has radius t. So the three red circles all have radius r, the two smaller circles have radius s, and this bigger one here has radius t. Alright, so the famous math problem number 14, the one posed by Sato in 1847, is if we assume that this rectangle here actually is a square, so if BDEF is a square, show that the radius of this bigger circle t is exactly twice the radius of this smaller circle's s. The difficulty level is probably between 2 and 3, so it's a problem that you can probably relatively easily solve in a day or a couple of days if you give it some thought. So I encourage you to now have a go at this problem. Turn the video off, have a pause, go off for a little while and see if you can solve Sato's challenge. Try to show that the radius of this circle is twice the radius of this circle. And all you're given is that this is a right triangle and that this figure here is actually a square. Alright, so to give you some hints that will be no doubt useful in solving that problem. Let me just remind you of, first of all, Pythagoras' theorem, which is the most important theorem in mathematics. And here I'm going to give it to you in not my favorite way, but in the kind of traditional way that you see most of the time. You have a right triangle here with side lengths A, B, and C. I prefer to work with the quadrances, which are from rational trigonometry, but you will be familiar with the traditional length version. And then Pythagoras' theorem says that in such a right triangle we have a squared plus b squared equals c squared. The other thing that is useful to know is maybe what we might call the in-center formula. A formula for the in-center, the radius of the circle that just fits inside the triangle, touching each of the three sides tangentially. So if we call that radius r, so that means from the in-center, usually denoted I, that distance is r, that distance is r, that distance is r. Those three perpendicular distances to the three sides are all r. And we're still talking about the case where we have the same right triangle A, B, C. Then the formula is that the area of the triangle, delta, if we take that and multiply it by 2, then that's the product A times B. And it's also the product of the radius, the in radius r, with the sum A plus B plus C. And why is that? Well, it's just the area of the triangle. So if we divide everything by 2 here, then we get the area of the triangle is A times B over 2, which is Euler's familiar formula. And then over here we would get, well, it's just the sum of this triangle, which is base times height over 2, so A times R over 2, plus the area of this triangle, which is B times R over 2, plus the area of this triangle, which is C times R over 2. That's why we get all those three terms there. So it's just an immediate consequence of just looking at the area of the triangle subdivided into these three subtriangles formed by joining the vertices to the in-center. Well, so that's a useful formula. We see that in the case of a right triangle, at least, we can solve for the radius immediately if we know the three side lengths. So it might be a little bit of a hint to help you out in solving the problem. Have a go. So here's a solution, a classical solution using standard techniques of geometry. The first thing we might do is to look at this square, because that's the assumption that this thing is a square, and have a look at these two kinds of circles that are appearing. And the property that this thing is a square, we can see that that determines a relation between the radii r and the radii s of these circles. If it's a general rectangle, then we can't really say what the relationship should be. But if it's going to be a square, then these two circles here are determined by symmetry, and these two are determined by symmetry, and there must be some relation. And we can determine that relation by looking at the little triangle formed by the centers, say, of these two circles and the center of the square where these two red circles touch. There's that same triangle a little bit bigger now. And the sides of that triangle, it's a right triangle of course, are, well, this one here is r because that's the radius of the red circle. And what about this length here? Well, think about this length in terms of the length from the center to the side minus the radius of the circle S. So this distance here is the same as this distance here because it's a square. And this is 2r. Right? So this is also 2r. And so the side that we're seeing here is 2r minus s. On the other hand, the hypotenuse of this right triangle, well, here we have two circles which are touching because this is a line between their centers. And so this is r, the radius of the one circle, and this is s, the radius of the other. So the hypotenuse is r plus s. And then Pythagoras tells us that there must then be a relationship between these three sides, so that r squared plus 2r minus s squared has to equal r plus s squared. Well, let's expand that out. So we have an r squared. When we expand this, we get 4r squared minus 4rs plus s squared. And on this side, we'll have r squared plus 2rs plus s squared. And conveniently, the r squared plus s squareds on both sides cancel. The 4r squared here We can isolate that by bringing the 4rs to the other side for a total of 6rs. Then we can cancel an r, because r is not going to be 0. We can also cancel a 2, and we'll get r equals 3s over 2. That's the relationship between the radius of the red circle and the radius of this smaller circle s. R is equal to 3/2 of s. Now let's have a look at the triangle CDE, which is sitting on top of the square. Okay, that's a triangle whose incenter is the same size as the two circles that were in red inside the square. Namely, it has a radius of r. So what do we know about that triangle? Well, we know its base is just the top of the square. And in terms of r, that's 4r. It's the same as the height of the square. The height of the square is the sum of the two diameters of those red circles. Each of them has radius r, so diameter 2r. So altogether it's 4r from the top to the bottom of the square, and so it's 4r across the side of the square as well. So in this right triangle, we know one side, which is 4r, and we know the in-center radius, which is r. We would kind of like to know what the other two sides are. Because it's a right triangle, we really only need to know one other side, and then the other one will be determined by Pythagoras' theorem. So let's call this length x, and let's call this length y. Then the in-center formula that I wrote down relates the three side lengths to the in radius. So it was here, 2 times the area of the triangle is first of all 4r times x, and that's also equal to the in radius r times the sum of the three side lengths, 4r plus x plus y. Alright, so now in this equation we can cancel the two r's on either side, and there's then a 4x on this side and then a single x on this side. When we bring it over, just be 3x on the left hand side. And on the right hand side, all that will remain is 4r plus y. So that's a relationship between x and y involving r. Now we still want to use Pythagoras' theorem, so let's use Pythagoras' theorem, which says that 4r squared plus x squared equals y squared. But from the previous, we know that y can be written as 3x minus 4r. So we get equals 3x minus 4r squared. That's then going to be a relationship between just r and x. Okay, so what do we get? Well, the 4r squared here will cancel with the 4r squared that will be on this side. So we're going to cancel those, and then there will be an x squared left here. And on this side, when we expand this out, we're going to get the square of the first term, which is 9x squared, minus twice the product, which is minus 24 times xr. And we've already canceled that third term with this one here. Alright, so now we look at this relation, say what can we do with that? Well, we can combine the x squared with the 9x squared to make 8x squared. And there's an x in all three terms, so we could divide out an x because x is non-zero. So then that would be that 8x equals 24r. Or if we divide by 8, it would be that x equals 3r. So that pleasantly simplifies to x equals 3r. And then if x equals 3r, then 9r equals 4r plus y. That means that y has to equal 5r. And then we see that the triangle that we're getting has sides 4r, 3r, 5r. This is just a 3, 4, 5 triangle. This is one of the aspects of this problem that makes it a little bit interesting, is that this relatively famous right triangle is appearing here naturally as a consequence of the assumptions. It also allows us to solve the problem now. So here's the original problem again, and I remind you we're trying to find the ratio between this t and this s here. Okay, we now know this is a 3, 4, 5 triangle. That means, because of similar triangles, that the whole triangle is a 3, 4, 5 triangle in ratio. And this triangle is similar to this triangle here. So the ratio of this incenter to this incenter, T over R, is going to be the same as the ratio of this side of this triangle with the corresponding side over here. So EF over CD. Should be another line there. There we go. And EF, well, that's 4R. That's the side of the square. And CD, we've just determined, is 3R. And the ratio is 4 over 3. So the ratio of T to R is 4 over 3. So T equals 4/3 of R. And we saw on the previous page that R equals 3/2 of S. If we multiply the two together, we get T equals 2S. And that solves the problem. Very elegant and pleasant, and a nice configuration. A little bit of a surprise that we get the 3, 4, 5 triangle appearing there. So the regular viewers of my channel will know that I'm a big fan of rational trigonometry, which is a much simpler and more elegant and more beautiful way of thinking about, well, geometry generally, but trigonometry specifically. And so it's a natural question, well, how are we going to solve the same kind of problem with rational trigonometry instead of standard geometry? In particular, how do we frame the problem so that we don't talk about lengths, but talk about the rational analogs, which are quadrants instead? That's a pretty interesting question, and I'm now going to show you how to do that. So this is just an alternate way of thinking about the problem within the framework of rational trigonometry or universal geometry. And because it's that framework, it's actually much more general framework that applies to other fields, in particular finite fields. This is a bigger picture than the one I've just showed you. But there's a price to be paid. It's algebraically a little bit more subtle and complicated, but as a prize, we see that our understanding increases when we look at this solution. So in rational trigonometry, we try not to talk about distances or length. We rather work with the algebraic analog, which is the quadrants between 2 points. And quadrants between 2 points in the plane is just the sum of the difference between x coordinates squared plus the difference in y coordinates squared. So the usual distance or length is the square root of the quadrants. So here is the problem now sort of restated, it's the same picture, but now instead of talking about radii of circles, we're going to talk about the quadrants of circles. So this capital R here represents the square of the radius. We have capital R there, there, and there. Here the quadrant is capital S. Here the quadrant is capital T. And so again, the problem at least can be stated completely in rational trigonometry terms. Just what's the relationship between this quadrants of this big circle with the quadrants of the smaller circle? What's the ratio between capital T and capital S? And as before, we'll just proceed as before. So we'll have a look at this same triangle again, formed by those 3 points, and here it is again. Okay, so what do we know about this triangle? Well, this side here is capital R. That's the quadrants there. This side, let's call it Q temporarily, and let's call this quadrants P. Okay, we don't know what Q and P are exactly. But we do know that in this direction here, there's 3 collinear points. This one, and the one on the side there. And we know this quadrant here is S because that's the center of the circle and that's the point on the circle. And we also know that the quadrants from here to here, it's the quadrants from the center of the square to the boundary. Now, the square itself, and this quadrants here is the quadrants from here to here. Now, this is quadrants of R. This is also quadrants of R. So the quadrants from here to here will be quadratic. It's going to be 4R. So this is a quadrants of 4R. Similarly, this is going to be 4R. So we have 3 quadrants here, a Q, which we don't know, an S, which we do know, and a 4R, which we do know. On this side here, we also know that this quadrants from here to here is going to be R, capital R, and from here to here is capital S. So again, we have 3 collinear points, and we have 3 quadrants formed by those collinear points. Okay, so we're going to use the two most important formulas in geometry, in fact in mathematics, the Pythagoras' theorem and triple quad formula. In this triangle here, the Pythagoras' theorem tells us that this quadrant's R plus this quadrant's Q equals this quadrant's P. The less well-known formula, but also very important, the triple quad formula tells us what happens when we have three collinear points. The relationship between the three quadrants of three collinear points. And, okay, I'm just going to tell you what those formulas are. We'll talk about them some other time, or you can have a look at my Wild Trig series, which talks all about rational trigonometry. Okay, so along here, for example, we have these three quadrants, R, S, and P, and the triple quad formula tells us that one way of expressing the relationship between those three numbers is that 4 times RS minus R plus S minus P all squared has to be 0. It's a quadratic relationship between those three quadrants. And exactly the same way, there's a same relation here, that 4 times 4R times S minus 4R plus S minus Q all squared equals 0. Let's call these equations 1, 2, and 3. And we want to sort of solve, basically want to get rid of Q and P. So let's take 4 times equation 2 and subtract equation 3, so that these first terms will disappear. Right? If we take 4 times this and subtract that, that's going to disappear. And we're going to get 4 times this minus this. Well, this then here is going to end up with a positive sign. So 4R plus S minus Q all squared. And then we'll have minus 4 times this thing. Minus 4R plus S minus P all squared. So this relation has to be true. And this is a difference of squares, because 4 is a square. So we can also write it as this minus 2 times this, or this plus 2 times this. And we can factor it. And you can check that. That's what I've done here. I've just factored this difference of squares into its two linear factors. 2R minus S minus Q plus 2P, and 6R plus 3S minus Q minus 2P equals 0. So at this point, all what we know is that either this is 0 or this is 0. Let's have a look at both cases. All right, so here are the two linear equations that we get by factoring that previous equation. Let's have a look at both of them. So in this equation, we're going to simplify because we know from the Pythagorean theorem that Q equals P minus R. Here's the triangle again. Q plus R equals P, so Q equals P minus R. We can replace this Q with P minus R. When we do that, then we get 3R minus S plus P equals 0. All right, then the first equation that we had, and I'll just rewrite it here. There's 4RS minus R plus S minus P all squared equals 1. That was equation 1 on the previous slide. Then this becomes, well, 4RS minus, what's going to happen here? Well, this S minus P here, if you bring that to the other side, that's the same as 3R. So we can replace the S minus P with 3R, giving us altogether 4R all squared. And now here conveniently we can cancel R, we can cancel a 4, and we get S equals 4R. So if this factor is true, that S equals 4R. That means that that quadrant is 4 times that quadrant. And we can see that's not being reflected in the picture. So we really have to have a look at the other factor. Here it was. We're going to play the same trick. Replace Q with P minus R. Then it simplifies to 7R plus 3S minus 3P equals 0. Then again, the same equation becomes, when we replace S minus P now, from here, we can replace it with minus 7R over 3. All right? So this S minus P is replaced with minus 7R over 3. We're just solving for S minus P in this equation. Well, this term here is a 3R minus 7R all squared. That's 4R all squared. And there's a 3 squared on the bottom, or a 9. So we can cancel an R as we did before, and we get 4S equals 16r over 9, or S equals 4r over 9. And if we want to flip that around, we could say that r equals 9s over 4. Well, that's more in keeping with the geometry of things. R is equal to 9s over 4 is now giving us the relationship between this quadrants of that circle and the quadrants of this circle. And it's really the same as what we got before in the classical case, where we got r equals 3/2 over s. This is just obtained from this one by squaring everything. So we've recaptured this. We've had to do a little bit more work. And we've actually seen that there's a kind of an alternate route algebraically. There's a suggestion of some other kind of solution, but it wasn't relevant to us for our problem. All right, so now we come to the interesting issue, which is this in-center formula. So for a right triangle, we already talked about this simple relation that tells us how to get the in-center, little r, from the three side lengths, little a, little b, and little c. What is a rational trigonometry or universal geometry analog of that formula? How do we restate that? How do we get that content, but without the square roots which are implicit in these lengths? Well, what we want to do is we want to rewrite this in terms of the associated quadrances, which are the squares. So what we're going to do is we're going to define capital A to be little a squared, capital B to be little b squared, and capital C to be little c squared, and capital R to be little r squared. And we're going to try to rearrange this formula to obtain a formula or relation between capital A, capital B, capital C, and capital R. That will then be the universal geometry analog of this formula. We can also establish such a formula in an independent way, but I think it's instructive to take a classical formula like this and see how we manipulate it to get a universal geometry formula. It's a very useful technique. And along the way, we'll keep in mind this relationship between the quadrances. So once we get the quadrants capital A of this and quadrants capital B there, then A plus B is going to be the quadrants capital C on that side. So the relation A plus B equals C is one that we can use anytime. All right, so how are we going to get rid of the little letters and just have big letters? We're going to square things. That's the basic philosophy. Okay? So we're going to square this relation. When we do, we get capital A times capital B, and we'll take the capital R that's appearing here and divide by it. And then the square of this will be, well, the square of A is capital A, square of little b is capital B, square of C is capital C, plus twice the various products, twice AB plus BC plus AC. So this is the simplest case of the trinomial theorem. You need to know how to square A plus B plus C. That's what we're doing. Okay, so we're happy with the capitals. We're not so happy with the little letters. We're trying to get rid of the little letters, but still have a true relation. So our strategy is we're going to put all the capitals on one side, and then we're going to square the side that has the little letters. So I'm going to take A, B over R. I'm going to subtract this A plus B plus C. And along the way, I'm going to replace C with A plus B. So this is really just 2A plus B. So that's on that side. And then I'm going to divide by 2. And I'm going to square both sides. Okay, so the 1/2 becomes a quarter. Now this whole quantity is squared. And now I'm going to square this AB plus BC plus AC. That's what's appearing here. It's the square. So what is that square? Well, little ab, we're going to square that. That's capital A, capital B. The square of this is capital B, capital C. The square of this is capital A, capital C. Now we still have to deal with twice the products. All right, so plus 2 times. What's the product, say, of these two terms? There's a little a, B, C. Well, the little a times the little a is a capital A. And we still get little b, little c. So this is the product of these two terms. Similarly, the product of these two terms is capital B times little a, little c. And the product here is capital C times little a, little b. Okay, again, we're in a similar kind of situation. We've gotten more capital terms, but we still have some little terms, little letter terms. So we're going to do the same thing. We're going to get them all by themselves, and then we're going to square things. We're not afraid of a little bit of algebra, are we? No, in fact, we like to do some algebra. Algebra is the tool that we can actually use to actually do things. So we're happy when we can make algebraic calculations. So we've got the left-hand side that we had here. We're going to subtract this part of the right-hand side, and we're going to rewrite it while we do that. So the c here, so it's c times a plus b. We're going to replace the c with another a plus b, making this really a plus b squared. Okay, so we're going to bring that to the other side, so we have minus ab plus a plus b squared. And all of that, we're going to divide by 2, and then we're going to square it all. The dividing by 2 gives us a quarter, and then we've got all of this all squared. That's going to then be equal to this quantity squared. I've rewritten it. Okay, that thing's squared. Now we have to square this. Well, square of the first term. A squared times capital B times capital C. Square of this, B squared times capital A, capital C. Square of this, C squared times AB. And now twice the products. Okay, what's the product, say, of these two terms? Okay, let's have a look at the product of these two terms. There's a capital B and a capital C, and the two little a's multiplied together is going to give us a capital A. So we're going to get a capital A, capital B, capital C times what's left is little bc. I guess it's that term there. So we're going to get an ABC times a little bc. When we multiply these two, we're going to get capital A, capital B, capital C times little ab. And when we multiply these two, we're going to get capital A, capital B, capital C times AC. Oh my goodness, you say, well, we still have little terms. That's true. But now some magic conveniently comes to our aid. Have a look at this right-hand side. It has a common factor of A, B, C. If we pulled out that A, B, C, what will we have left? There would be an A plus a B plus a C plus a 2 times AB plus BC plus AC. That's exactly what we have right here. Right? So if we take this right-hand side and we pull out a factor of ABC, then what's left is exactly AB over R. So we don't have to square anymore. We just use a previous equation that we've already established. Much easier. And now, lo and behold, this simplifies to a squared, b squared, a plus b, because we can get rid of the c, a plus b, over r. On the right-hand side, and on the left-hand side, we had this expression here, and that only has a's, b's, and r's in it. Capital A, b's, and r's. So this equals this is a relation between capital A, capital B, and capital R, which no longer involves the little numbers A, B, and C. It doesn't involve C anymore. So now we have a relationship between the quadrants here, and the in radius quadrants, which is much the same as we have over here. Except here the relation, there's a C, would actually have to be represented by a square root of a squared plus b squared if we want to write R purely in terms of little a and little b. All right, this is a quartic equation for R, A, and B. Okay, there's some denominators here, but the denominators are basically R, so we can multiply through by those denominators. And you can see that we've got this quantity here, it's squared, and then some more stuff, and we're squaring it again. It's going to be a quartic polynomial expression. If we clear denominators, set this equal to this, clear denominators, put everything on one side, then we're going to get a polynomial of degree 4 equals 0. All right, so you might like to check the algebra here. Okay? So it's an exercise. Show that this quartic relation obtained from that previous derivation, once we clear fractions, can be expressed exactly this way. Now I'm going to introduce this polynomial f of a, b, r. It's defined here. So it's 16r to the fourth minus 32a plus b r cubed plus 8 times 2a squared plus 3ab plus 2b squared r squared minus 8ab times a plus b r plus a squared b squared equals 0. So that's the quartic relation between, well, the in radius quadrants R and the two shorter quadrants of a right triangle, A and B. And it's probably the first time that this has been written down. So there you go. A new result. And now the second exercise, I'm going to ask you to show that in the special case when the side A is 16R, that's actually the triangle that we're interested in, right? Has in quadrants R and the bottom quadrants was 16R. That when you then replace this capital A with 16R, the whole formula magically simplifies. It factors as 16r squared times 25r minus 9b times 9r minus b. So that if this thing is equal to 0, then either this is equal to 0 or this equals 0. So either b equals 9r or b equals 25 over 9 times r. So that's, if this is 16r, then either this is 9r or it's 25 over 9 times r. And it's the first solution that we want because that's giving us the 3, 4, 5 triangle. If this is 16r and this quadrant is 9r, it means that this is in the ratio of 16 to 9. It's the quadrants analog of the 3, 4, 5 triangle. In terms of quadrants, this would be 9, 16, 25 triangle. So we're getting that same relation that we did with the classical geometry, albeit through some much more extensive algebraic calculations, and along the way, suggestions of some other solutions that may have some relevance to the situation. All right, we can now finish the problem exactly as before. Once we have this, then we have that the ratio between the similar triangles is exactly the same kind of situation. Then t is going to be 16r over 9, and we've already established that r equals 9s over 4. When we multiply them, we get that t is equal to 4s, which is equivalent to the little t equals 2s solution to the classical situation. So those of you not too familiar with rational trigonometry might ask, well, isn't this overkill? We got this quartic equation here where the classical solution only had a linear equation for the in radius. Isn't this a lot more complicated? Well, it is a lot more complicated, but it's also a lot more insightful, and it's a lot more general as it turns out. We can understand this by thinking about not just the in-center, but the x-centers of the triangle. So a triangle really has 4 in-centers, not just one. They're usually called x-centers, but I like to think of them all as in-centers and more or less equivalent. So if you have a triangle like this, and you look at angle bisectors at some vertex, well, there's an angle bisector, but this perpendicular line is also an angle bisector. Okay? So you actually have two angle bisectors at each vertex. And if you look at those various angle bisectors, they meet 3 at a time, not just at this in-center, but also at these in-centers here. Allow me to call them all in-centers, because algebraically there's not so much difference between them. In our picture it looks like this one is special, but algebraically they all sort of on an equal playing field. And this quartic equation here is reflecting that symmetry between the 4 in-centers. It's giving you a formula for all 4 in-center quadrants at the same time. You're getting more than you bargained for. This is a quartic equation, and its 4 solutions are quadrants here, quadrants here, quadrants here, quadrants here. because the algebra does not want to treat this circle in a dramatically different way than these circles here. It's a very important insight. This is often what you're getting with rational trigonometry. You got some higher degree equation. Chances are there's some extension, some other aspect of the situation that you can't see because maybe you're only focusing on some small part. But the algebra is telling you to look in a bigger way, saying, broaden your mind, have a look around, there's more there than what you're just looking at. So to emphasize that point, here's another very interesting exercise for you to do. It's to have a closer look at the 3, 4, 5 triangle, or in terms of quadrants, the 9, 16, 25 triangle. So if we take that same polynomial relation between the two shorter quadrants of a right triangle and its in quadrants, R, then see what happens when you replace A with 16 and B with 9. So we're looking at the special case of this 3, 4, 5 triangle. Quadrants of 9, quadrants of 16. Then the polynomial, degree 4, factors like this. As 16 times r minus 1, r minus 4, r minus 9, r minus 36. Now when you get this kind of factorization in this situation, you know that you've more or less done the right thing. You're looking at things the right way. Right? This is like some gift from God or something. Okay, it's a beautiful thing. It's telling us that the in-center quadrants of a 3, 4, 5 triangle are 1, 4, 9, and 36. And here they are here. So in terms of lengths, back to the original thing. That's a length of 1, that's a length of 2, that's a length of 3, that's a length of 6. Or that's a quadrants of 1, a quadrants of 4, quadrants of 9, quadrants of 36. So if you'd like to know a little bit more about this fourfold symmetry between the incenters, it's really just the start of a really dramatic, lovely picture in triangle geometry. I recommend this paper that a student of mine, Nguyen Le, and myself wrote, published last year. Okay, it's called Universal Affine Triangle Geometry and Fourfold In-Center Symmetry, and appears in the lovely journal COG, the journal for the Croatian Society of Geometry and Graphics, number 16, 2012, and there's the pages. So there you see triangle geometry laid out in a very systematic, broad way using this framework of universal triangle geometry. So we want to try to move in the direction of Clark Kimberling's encyclopedia, but from a rational point of view. We'll talk more about that kind of thing probably in some other problems. There's lots of interesting problems associated with triangle geometry, of course, a very rich subject. Finally, here are a few references that you can have a look at, chase up on some more examples of Sangaku. So there's lots of interesting problems. It's an interesting mind for challenging and original problems. And I'm going to be talking about some more of them in this series at various later points. So first of all, there's a lovely book, Sacred Mathematics, Japanese Temple Geometry, by T. Rothman and H. Fukagawa, Princeton University Press, 2008. A website, www.wasan.jp by Hiroshi Kotera, which contains large lists of Sangaku. There's Alex Bogomolny's wonderful geometry site, Cut the Knot, which is a must-see on any student of geometry's list. It's a very extensive collection of wide variety of geometry problems of all kinds, but in particular he has sections where he looks at a lot of different Sangaku in great detail. This is a lovely site, and he's made a very important contribution here. There's an article by Tony Rothman, Japanese Temple Geometry, which appeared some years ago in Scientific American. And you can also have a look for the very original modern work of Hirotaka Ebisui, who is currently developing all kinds of original Sangaku type problems. And we're going to be talking more at some point in this series on various problems that he's posed and solved. Very interesting development. Okay, so in our next video in the series, we're going to look at another famous math problem, going back to Leonhard Euler. Again, many problems go back to Leonhard Euler one way or the other. And this is the problem of understanding the Platonic solids and the relationships between the numbers of vertices, edges, and faces of a Platonic solid. Very famous problem that had many consequences. Still has many consequences. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.